So the binomial theorem is a procedure that allows us to expand binomials effectively. Now, one of the biggest contributors to the binomial theorem is Blaise Pascal. He was a physicist, a theologian, and as well a great mathematician. Now, one of the things that they were all trying to do was what is the most efficient way to properly expand a binomial expression. This triangle is constructed by starting with a 1 in the upper left quarter, so at the beginning like this, and then each number in the triangle is a result of adding the number to its left to the number above it. Pascal used this triangle for many things. One of them was to help provide a solution to division. Today we see this triangle used most heavily with probability, combinatorics, or permutations and combinations, and binomial expansion. So imagine you start with a 1 here, and then on each side there's a 1. The sum of those numbers is 2, and once again we repeat the idea that on the outside, or the outermost side of each line, there's going to be a 1. Now, if I take these two sums, I get 3, as well as this one, 3, and then once again, I'm going to end off with a 1. This continues on to the next row where the sum of 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4, and then of course, we end with the 1s on each side, on the outside. Now, we're going to do the same thing for the 5th row, where 4 and 1 is going to be 5, 4 and 6 is going to be 10, 6 and 4 is going to be 10, 4 and 1 is going to be 5, and then of course we are going to end off with 1s on the outside. And before you know it, we have a system where numbers are counted in an array that forms a triangle. Now, when your counted numbers are arranged in such a way, there's a lot of cool things that can happen here. One of them is that the rows that this breaks down into can represent the degree at which your binomial expression is held to. Row 0 would be the degree of 0. Row 2 would be to the degree of 1. This would be to the degree of 2. And then it goes all the way down this, and this could technically continue on infinitely. Another cool thing is that the number of bubbles or circles in each row, so for example, if I look at the second row here, n is equal to 1, I have 2 circles, represent the number of terms in the final expansion. So, for example here, let's say I had x plus y, and that was to the 0. Well, I know that if I were to expand this, meaning I would apply the exponent outside the bracket to everything inside the bracket, anything to the exponent 0 was equal to 1. So you'd have 1 plus 1, which would simplify to 2. And that is, like the number suggests, only one term in the final expansion. If I look at 1, so let's say I put something to the degree, same binomial, but to the degree of 1, well, that 1 would apply to everything here, and it would simplify to x plus y. And like Pascal's triangle suggests, there are 2 terms in the final expansion of a binomial that has a degree of 1. And so then using this triangle, I can kind of simplify or jump to the fact that if I have a degree of 2, I know that my final expansion is going to have 3 terms. If I have a degree of 3, it'll be 1, 2, 3, 4 terms. Right over here, if I have a degree of 4, it'll be 1, 2, 3, 4, 5 terms, etc. Lastly, the numbers themselves in the circle. So let's say if I have a binomial that is expanded, to the 3rd degree here. These numbers, and I'm going to kind of dot them in sort of a fuchsia color here. The 1, the 3, and the 1. These numbers themselves are what each term is going to be multiplied in the final expansion. So to kind of sum it all up here, the rows represent the exponent that, or the degree that your binomial is being held to. The number of bubbles in each, or circles in each of these rows, tells you how many terms there are going to be in the final expansion. And then the numbers in those circles are going to tell you what each term will be multiplied by if you expand things correctly. So you can essentially use Pascal's triangle as a method or a shortcut to expand large binomials. So let's say I'm asked to expand x plus y and then close brackets to the 3. Well, what I could do is I can go right to the 4th row where we could see that it corresponds to the degree 3. And I can see that there are 1, 2, 3, 4 terms. So I'm going to write xy plus xy plus xy plus xy 4 times. Okay, now what I'm going to also do, I'm going to rewrite this again. But this time I'm going to stick the coefficients that I see over here in front of the terms. So the first one, x times y, has a 1 in front. The next one has a 3, so it'll be 3xy. The next one also has a 3, so it'll be plus 3xy. I'll put this in the right color here. And then the last one is just going to be plus xy. Now, if we think about x as the a and y as the b, we're going to now insert our exponents into this expression here, starting with the highest degree of a corresponding to the lowest degree of b. So that would be x to the 3 and then y to the 0. And then 3x to the 2, y to the 1. So as our x decreases by 1, your y is going to increase by 1. Then times 3x to the 1, y 2. And then x to the 0, and then y to the 3. And then we're going to simplify. We know that anything to the 0 is going to basically just become a 1. And so when I cross out those, or I can put a 1, my final expression was x to the 3 plus 3x to the 2 y plus 3xy2 and then plus y3. And I was able to do this without any calculators, without any foiling or expansion, and this was all based on the triangle. So it really helps speed up the process of expanding this binomial. So let's expand c plus d to the 4, and we're going to do the same thing like we did last time. We're going to go to the degree 4, and we're going to count 1, 2, 3, 4, 5 terms. So we're going to go here, and I'll do it in purple. It'll be CD plus CD plus CD plus CD, and then the 5th one plus CD. Now, one thing I probably should have mentioned in the previous example, why are we adding plus and not minus? Well, that's because the sign here between the two variables is plus. When it's minus, we'll show you what to do then. So now, just like in the previous example, we're going to insert the coefficients that it shows us. So the first one has a coefficient of 1. The second set has a coefficient of 4. The third set has a coefficient of 6. And then it's 4 again, and then 1. And I'm going to add the exponents again, beginning with the highest on the c. So if it's to the degree 4, that'll be 4 on the c while d has a 0. Then it'll be 3 on the c while d has 1. Then 2 on the c while d has 2. And then 1 on the c while d has 3. And then 0 on the c while d has 4. And like we did previously, anything with 0 simplifies to a 1, so we'll get rid of those. And our final expanded expression here, and I'll write it over here, is going to be c to the 4 plus 4c3d plus 6c2d2 plus 4cd3 and then plus d4. And again, using our Pascal's triangle, we were easily able to expand this without much foiling at all.